Okay, to start the presentation today, we're going to look at some of the things that you can do for teaching hybrid and electric vehicles in the class. So we know that this is occurring now either in the high school or the community college level. Some of the various things that you need to look at. We've got some of the main topics that we need to look at. There's different standards around the world, but of course what you need to look at on all of these vehicles is basically the same thing. So we're going to cover some of the safety topics, the various topics within the battery, drive systems, so looking at inverters, motors, and the various things there. We've got some of the various standards here, so we'll have a look at, say for instance, ASE L3 standards. If you have a look at these, there's a very high standard put on safety and also system understanding, and also some of the main common faults that you would find within hybrid electric vehicles as well that you need to test for. So insulation testing and especially shutting down the vehicle. So we'll be going through that today and showing you what we can do together with some of the equipment that you can have in the classroom, but also what you can have, for instance, with this piece of hardware and software that we've got. We'll show you. Okay. So, taking it right back to some of the basics, the fundamentals. So what type of vehicles do we see now as hybrid and electric vehicles? So, of course, basically all forms of transport now are becoming electrified, or some of them have been for a long time now, but you see that more and more manufacturers are becoming electrified. You see some of the countries, it's making it on the news a lot now. So Norway, they say within 2025 all vehicles must be electric, or banning diesel in some other countries. France will say in 2040 they're shutting down all combustion engines. Volvo from 2019 will be only producing electric vehicles. So it's when they say they'll only produce electric vehicles, all new models will be electric. So they'll be continuing the combustion engines, but when it's time for a model upgrade, only electric vehicles. So you see this is becoming more and more common. We're not going back, it will be becoming electrified. So it's important that we, as teachers and instructors, know what we can do to teach the next generation of technicians to come through so that they can, one, be safe, but also to help diagnose and repair these vehicles without wasting too much money. So you see all the different types of vehicles. Now, one of the more important things is how do we recognize these vehicles as well? So it's not just a matter of, okay, understanding or knowing, okay, Prius is pretty obvious, they're all electric, as in all have an electric motor at high voltage, also have a combustion engine of course, but how do we recognize some of the other ones where you have a combustion engine and also an electrified version, which is also becoming more popular now. So often what you see within a lot of the manufacturers, they'll have the blue, what's known as the blue badging. So just where you've got the normal badge, so for instance Toyota, inside there'll be this blue glow. The Lexus, Volkswagen, a lot of the manufacturers do this. It's not a standard, it's not an industry standard, but you find a lot of manufacturers do it. So that's one of the first ways to identify these vehicles. Obviously then try and look for any specific badging, hybrid vehicle, we've written on there, or zero emissions, that sort of thing. So you'll try and find that. Also in place when you've got a pure electric vehicle, where what looks like the fuel filler cap will be a section for plugging in the vehicle. The instrument display is also a good example of how you can identify the vehicle. So a lot of these vehicles have a battery indicator as opposed to a fuel indicator. Every vehicle will be different, but there'll be some sort of way of recognizing that. And of course, when you've got an electric vehicle, you might just see that there is no exhaust pipes. So again, pure electric vehicle, not going to work on a hybrid vehicle. Within the vehicles themselves, so once you open the hood or the trunk, look under the seats, you might begin to see some of the various other symbols that we see here. So again, manufacturers tend to have their own type of markings or stickers that you'll see, but any high voltage components will be having the caution, attention, some sort of system that will tell you that it's a high voltage system, especially with the triangle with the lightning bolt in it. That's on the main components themselves. So on the battery, on the inverter, you'll see it on the hood. It'll be different areas like that. So somewhere that's visible. Now, of course, when we've got some of the other sections, we'll be seeing orange cables or orange coverings. So inside the vehicle, you begin to see orange coverings, which will be then covering the orange cables, but you'll see that in various different points as well. So even if we have a look at this Prius, underneath the seat, even though the battery is in the back of the vehicle itself, there's little sections where you find the cabling going through, so that's also the high voltage cables going to the front. So obviously anything orange is then high voltage. Another thing about electrified vehicles is the ready light and how that is shown on the various vehicles. So the ready light, most of you will know Toyota use ready light, a lot of vehicles use ready light. You also have this here, which is the little vehicle with the arrows going in it. Now that's equivalent to key on, engine running. So the vehicle is literally ready to drive. So you'll see with the ignition display here that you can also have, if you don't press the brake pedal, when you press the ignition on, you'll get the condition key on, engine off. And so the vehicle is obviously not ready, but all of the lights will be on the vehicle. When the vehicle is ready, then of course you need to be aware. Very important when you're servicing. So the combustion engine can start straight away when the battery level is low. So that's happened many times in the workshop where the technician has driven the vehicle in, because the engine is not running, they've parked the car, and then all of a sudden the combustion engine starts when they're not ready. So when the battery level gets low, the combustion engine will start trying to charge up the battery again. So you need to be very careful. So obviously the old urban story of the Prius technician driven the vehicle on the hoist, put the vehicle up in the air, drain the oil from the engine, and all of a sudden the engine started, and started without oil. So vehicle stuck up on the hoist. Very important for your students to understand that and be aware of the situation. Nissan, for instance, uses the other type of ready light, the little vehicle. So just be aware of the different types. Some of the classifications of different vehicles. So it's very difficult to standardize, so to say, the various types of, especially hybrid vehicles. Electric vehicles are easy. Electric vehicle there is no difference. They all have a battery and usually one motor, or if you've got normally a sports car type vehicle, they'll have wheel motors, for instance, but most of them will have the MG2 just to drive the vehicle. When it comes to hybrid vehicles, that's another story. So some manufacturers will call their vehicles with a combustion engine, they'll call that an electric vehicle with a range extender. So, for instance, the BMW i3, even the Chevy Volt, they'll consider that, General Motors consider that an electric vehicle with a range extender, for instance. So there's so many different types of hybrid vehicles available now, how they work in conjunction with planetary gear sets, or is it just on a boost type function for the combustion engine. So there's different types. So what we call here the type 1 is very similar to the Prius. So we've got integrated combustion engine, MG1, which is purely as generation, so it's not used for driving anything. The only time it is used as a driver is a starter motor for the internal combustion engine, that's all. All of the drive is then considered coming through MG2. So MG2 is always operating to drive the vehicle. Type 2 hybrid. Now again, this is different countries, different people, different manufacturers. What we call this a type 2, this could be called a parallel hybrid. The one before could be called a series parallel. Toyota call it themselves a series parallel. This type here is your is like the Honda IMA type system. So the motor generator is acting as a booster for the internal combustion engine. Again, there's different types that act with inside this. So could be a clutch inside of the system which separates the motor generator from the internal combustion engine, so you could drive with one or the other. And then you've got what's called the Type 3, and this is now working with clutches in between the systems as well, so that it can also be separated, the way that they turn on, turn off, and which direction of flow the energy is going through. That's another type of system there. You've also got fuel cell type vehicles, obviously pure electric vehicles. Belt alternator starter systems are also included as a micro hybrid, some people like to call them. Sometimes they're running 48 volts. Now that doesn't use the orange cables like you do on a hybrid vehicle. You often see the yellow cables for that, sometimes blue cables. 48 volts, you can see that will become more popular as well, even as the drive motor in vehicles. So that's the next development for vehicles, is you'll be seeing 48 volts on also the drive motor. So not just on the belt alternator starter, it will also be more along the lines of this year you'll see a 48 volt drive motor helping the combustion engine. The reason they're using 48 volts is, one, it's now looking at a larger 12 volt system, but the threshold for high voltage is 60 volt. So we're staying well under the 60 volt system. So not being high voltage for DC, so we're staying under that, so it's safe. So looking at those in just a little bit more detail. Battery alternator system, how that will work. So again, this is using some of the different names that you might be familiar with for some of the different manufacturers. Now what you see here is also something interesting, is the battery size. The battery type and the battery size will change according to the type of vehicle that you have, or the type of hybrid or electrified vehicle that you see. So here we've got the mild hybrid, or the Type 2, and the battery will be usually a bit smaller, sometimes nickel metal hydride. Similar with the medium hybrid here is what we're calling with the clutch in between the two there. So similar to a Type 2, but with a clutch, so you can separate the two. strong hybrid or the Type 1 Prius type, it's actually also using a relatively small battery. So what's quite surprising about the Prius is you're only going to get up to 2 kilometers to 5 kilometers, so 2 miles to 4 miles range on pure electric mode. It's not really designed for driving in electric mode. It's designed for having the battery. The battery is then basically an accumulator which absorbs the energy from regenerative braking. That's basically the whole idea behind the Prius. It's not for driving for hundreds of miles on electric drive. It's basically just a large battery compared to say a 12-volt battery, but it's large in that it will accept the regenerative braking and then basically helping the combustion engine along. Now you see the difference here with the electric vehicle. The battery has to be much bigger. So in a lot of these vehicles, the battery will be basically the whole floor of the vehicle. I think most of you will be familiar with the size of the battery in the Prius, or if we have a look here, this is the battery case from a Q5, so an Audi Q5. So it's not big, but as I said, it's not there to take hundreds of kilowatts or loads of energy. It's just there to basically take the power from the regenerative braking. A pure electric vehicle, the only way you can energize these vehicles is by plugging it in. So they need everything. The only way they're recuperating is through regenerative braking or driving downhill. Now, somewhere in between those two is becoming a bit more popular is plug-in hybrids, and the batteries in those are now going also to lithium-ion. So you'll see that they're not quite as big as a full electric vehicle, but they're bigger than your typical hybrid. So the range on those now will be 40, 50 miles up to 80 to 100 kilometers. And so they're utilizing a little bit more of the plug-in, so using the network to drive the vehicle makes them much more efficient. So most people driving their 20 miles to work, or even if you're driving 50 miles, if you can achieve that in one version just from plugging it into the power outlet, you've saved all. Basically your combustion engine is not turning on at all. Now if we have a look at, say for instance, a driving mode of a typical hybrid, so how are the three integrated? So here we are, we've got the ready on, and just under gentle acceleration you see that the electric motor comes on. Then as we need more power, we're using more power from the battery, but also the combustion engine is on as well. I'll just go back here. So as we begin to brake, obviously we don't need the combustion engine right now, but we're using the motor generator as a brake. We'll go into that into a little bit more detail on how that works later. But basically, under first braking, the vehicle will use the motor generator completely to slow down. As we go further, if it becomes an emergency braking situation, we're not using the motor generator anymore, we will switch over to the hybrid hydraulic braking system. So that depends also on various things. Hydraulic braking can occur when the battery is full. So if the battery is full, the system will say, hey look, we can't use the generator, there's nowhere for this energy to go, so it'll switch to hydraulic braking, obviously slow down the vehicle in that way. Now, if we just have a look at some of the various drive modes. So what we've got here, this training system is, we're not trying to replace the vehicle in the workshop, but we're trying to basically give the student a place to practice and create a culture of safety, but before the student goes to work on a real vehicle. So as we know, some of these vehicles can be quite dangerous. So we want the students to learn as much as possible before they go onto the real vehicle. So this is going to help on one side for you as the instructor to say, okay, I'm now confident that the student can shut down the vehicle, isolate, make sure there's no voltage left in the vehicle before they work on it. You can make sure that they perform that procedure before they go on the real vehicle, but also it helps in a way to bring across the technology. What is behind these vehicles, what's inside, how do they operate, and that's something that can be difficult on a real vehicle. So it's one thing having a Toyota, Nissan Leaf, Chevy Volt, all of those different vehicles, but what's inside. So without really pulling them apart, looking inside, it can be quite difficult. It's also, again, quite difficult or quite dangerous to take some of those measurements on a real vehicle. So this just gives us a chance, gives the students a chance to look inside, see how they operate in a safe way. Then they step into the real world, in the workshop, and work on these vehicles. So what we've got the chance here to do is to simulate the various types of vehicles. So for instance, we've got them down on the side here. So obviously we can't do every type of vehicle now, but we've broken it down into the series hybrid, which is type of range extender. So a series, you see what I've done here is I've basically changed the overlay mask, which has different sort of holes here. So by doing that now I can switch the different type of vehicle that is displayed here. So I'm showing here an electric vehicle. Obviously now we don't have any motor generator 1, any combustion engine, so we're just showing that on the system here. So if you look at an electric vehicle, as we mentioned, there's only two things that we can do here. So we've got electric drive or regenerative braking, energy recuperation. If we go to the series parallel or the type 1 hybrid, which is the Prius with a planetary gear set. Now we've got lots of different modes that can occur within this vehicle. So just driving on pure electric mode, we can see the energy flow straight from the battery into the drive system. Also possible through the planetary gear set, for the combustion engine to partly charge the battery, but also use some of its power to help drive the vehicle as well. Something that we can do here is to change the state of charge of the battery. And see what conditions come on, the combustion engine will come on and operate. So this here gives the students just a chance to look through and see, okay, what's actually happening. So it just visualizes what's going on, what the power flow is. Now, of course, every manufacturer is slightly trying to change the way they do it, trying to outsmart patents, that type of thing. But this is the general idea. The technology behind these vehicles is basically the same. The way a motor is driven is the same for an electric vehicle as it is for a hybrid vehicle. So the technology is basically the same. The high voltage battery is there, the inverter needs to be there, the type of motor is also there. Even if it's an induction motor or a permanent magnet motor, the inverter still basically works the same way. So all of the different types of hybrids are shown here. So we've also got this the schematic. So basically just showing the very basic outlay of a hybrid vehicle. So we've got the high voltage battery right here. This section here is all considered DC, so to say. So we've got the inverter right here. This is where the DC voltage comes in, is then converted to AC voltage. MG1, MG2, so this is for a series parallel. And you can see, okay, what's the equivalent there? The inverter, MG1, MG2, 12 volt system is also charged from the high voltage system. Also some important notes there. So we've got what's called the buck boost converter. Now that is to, I'll just jump down here. So we see this is some of the typical voltages that you find within various hybrid vehicles or electric vehicles. And you can see here we've got battery voltage, so that's the traction battery. Now you see a lot of manufacturers will use the same voltage at the battery as they do at the motor. The exceptions here are usually Toyota, Lexus vehicles, so they'll use a buck boost converter. So that increases the voltage from the battery, so anywhere from around 200 volts to almost 300 volts. And you'll see the voltage will increase up to 650, almost 700 volts. And that's not always the case. It's not exactly always 600. It's varying in between. I'll also go into a little detail about that as well soon. So that there is what we call a buck boost converter. So that's converting the voltage up or down. So in one direction from the battery, obviously up to the motor. But when the voltage is coming back or the current is coming backwards, then it needs to drop that voltage down again to charge the battery. Obviously, if we have 700 volts on a 200 volt battery, it will probably ruin your day. Now, when we go back to this wiring diagram, with the two DC to DC converters that you see here, the top one here is especially for the high voltage. So we've got the high voltage coming in from the battery, and then this is then converted to an even higher voltage for the traction motors, the traction motor. For the lower system here, this is to basically replace our alternator and is used for charging the system. Now, this system is very important that they're two completely different systems. This one needs to be what's called galvanically isolated. So it's completely isolated. There's no touching parts. It's using a transformer within the system, which is then basically wirelessly charging it's wirelessly converting the voltage to your normal 14.6 volts to charge the 12 volt battery. Very important. So that way we're also isolating this high voltage system, yet another system for safety within the vehicle. The AC compressor is also high voltage. Again, some of the older systems was a 3 volt system coming from the inverter, what we call the inverter in the vehicle for the MG1, MG2. Most of the systems now are using the DC, and the inverter is inside the air the air compressor itself. And of course, with electric vehicles and hybrid vehicles, we've got the charging port. So you see there that we've broken this up into an AC system and a DC system within the various types of vehicles. So again, if I have a look now at an electric vehicle, basically we've taken away one of the motor generators and we're just using here MG2. The rest of the system is exactly the same. This type of wiring diagram, of course every vehicle will be different, but the way it works will be always the same. Even with a fuel cell vehicle, so fuel cell vehicle, the way they work, obviously goes into a little bit more detail. That'll be time for another seminar, but just quickly, I remember back in the day when I was a young apprentice, I always thought, hydrogen vehicle, it's just burning hydrogen, but no, of course not. It's using a special membrane which passes hydrogen through the membrane and basically strips the electrons off, which are then used to charge a battery and drive the motor, just like on a normal electric vehicle. So they're working on direct drive hydrogen vehicles, but mainly it's about charging the battery, which then the vehicle drives as a normal vehicle. Now, for integrating this into the classroom, it's always important that we then take the knowledge that we've learned here into the real world. So I always recommend these practical tasks. So I'm hoping to have these as a handout available for you, but basically it gets the students to So for this one here, we're getting the student to identify some of the components. So if you're able to have an electric vehicle in your school or a hybrid vehicle, you can get the students to go and have a look and just identify. So again, this is right into the basics. Okay, where is the battery? Where is the inverter? MG1, MG2, the charging interface, that sort of thing. Just get them thinking about the types of vehicles that they're working on. Now, if we have a look at electric vehicles, there's a few extra things there that you'll find on electric vehicles that you won't find on a hybrid vehicle. You may find on a hybrid vehicle, depending on the type. But, for instance, where is the heating unit? So this one here, because it's an electric vehicle, there's no combustion engine to heat up the coolant in the conventional way for heating the cabin. So you often have a high voltage heating unit, which is a high voltage system with a large resistor, which then heats up the coolant and used in the conventional way. So sometimes they're hidden in the front of the vehicle where the engine would normally be. So things like that get the students looking around. Also, what I like to do when I'm teaching is to get the students to really think about the vehicles themselves. So I've made these handouts, which again, if you put your name down, your email address, I'll email these out to you. And you can give these to your class or a group of students at the time and just get them to look at the vehicle and say, okay, so service plug, where would I find that sort of thing? This one here, so your brake booster, this is one of my favorites. So go to a Prius and ask the students, okay, go find the brake booster. On the Prius, there is no brake booster, so it's using, on one side, the motor generator to slow the vehicle down. On the other side, it's using the ABS system. If there is any need for braking, it will use the ABS system to slow the vehicle down. So the motor and the pump inside the hydraulic system. things like this, you can get them to put the configuration down. Okay, MG1, power split device, MG2. So just lay that on the, for instance, on the vehicle itself to have a think about how the system is built. Water pump for the inverter. So there's a whole bunch of these. And as I said, if you put your name down, I'll email these out. They come on a sheet of paper, which you can laminate, cut in half, and away you go. Okay. Now, all of the different type of standards for teaching to electric vehicles around the world, they're all focused on safety. So safety is one of the biggest considerations. Obviously, when we're looking at electric vehicles, there's no room for error. So as we've seen before, we're looking up to 700 volts. It's just best to do things correctly. Now, one of the important things to learn is the isolation procedure. So shutting the vehicle down before you work on it, obviously. It's also good to understand why do you need to shut down the vehicle, shut down the high voltage system, what jobs do you need to do that. Things like that, shutting down the braking system as well, so before servicing it. Now, what we're doing here is basically, as I said before, we're creating a culture of safety, trying to get the students to really think about what they're doing before they go to the real car. So, one of the things, take off any jewellery, things like that. Now, if we're just going to shut down the vehicle, we've also got the key. It's also different things that you get here. So I've got a lockbox that we can use, or you can put the key into your pocket. But it's important that you follow the rules either for the manufacturer or for where you work. It's very important. So shutting down the vehicle, first thing is the key. If it's a smart key, so a key that you keep in your pocket, only need a press button, that key needs to be put away about 5 meters or 15 feet, thereabouts. So lockbox, something that you can lock up so no one can have access. I've heard a couple of stories where people have shut down the vehicle, but they left the key in, working on the vehicle somewhere else, all of a sudden comes in, tries to move the car, didn't see the person, the technician working on it, started the vehicle, and almost a disaster, but yeah, it really needs to be careful. We also need to be aware of all of our safety gear. So if we go through some of the different PPE, so gloves will be dependent on where you are around the world. So for the American standards, we've got the Class O type gloves, and they're rated up to 1000 volts. What you also notice with and it's particular to the US, is you've got the leather overgloves as well. Really good idea. So the leather overgloves are what go on top and protect the rubber gloves. So obviously they're very relatively fragile gloves, so if you catch them on a sharp edge, you can really damage them quite quickly. Gloves need to be stamped on them as well. So up here on the edge, it'll tell you when they've been tested, if they've passed, everything is on there. Needs to make sure they're up to date. Now there's various ways of testing these gloves as well. So if you look here, you can get some special little pump for putting them up. In an emergency, you can always do the old trick, the field servicing. Blow them up or roll them up like this. What I've found, however, is though, we've done some testing with the pump type of system that you've got here, once we've done that, we've actually put a little pinprick into this type of gloves under pressure, and it takes a good 5 minutes before you see the glove will actually go down. So obviously depending on the size, but that is, a pin has gone through the glove and very small hole. So it's not just a matter of checking, holding for 2 seconds or something. You really need to make sure that it's, hold on to it for a little while and make sure that those gloves are okay. Obviously, please get them sent out to the laboratories to do the testing when they're due. It always makes sense to have a few pairs of these in the workshop, especially at school. Have plenty of these around, because once they get sent out, they take a little while to get tested. Now, these are also, when they're tested in the laboratory, they've got a big hand made of copper that goes inside, which then they test with high voltage around it and seeing if there's any leakage in that way. So we want to check both of our gloves for condition, plus also to make sure that they're in date. Also, depending on who you work for, where you are, you might also be required to wear either a face mask or at least safety glasses. And they need to be ANSI for the US. Different standards apply for different countries around the world. If you're wearing overalls, also important to make sure that you don't have press studs on there. There's no metal within your, or zips or anything like that. Always use Velcro overalls or material. Even your safety footwear, so we're all used to wearing steel cap boots. Just be aware that you might have to use some sort of synthetic material or even overshoes that go on your boots. Some manufacturers make you have a shepherd's pole, a fiberglass pole, also to, if anyone is electrocuted and hanging onto the vehicle, you might need to use the fiberglass pole to pull them off. Again, depending on where you are and what standards you're following, you might need to have a lockout tags or lockout box. Now, a lockout box works in the way that the key for the padlock that you see on the lockout box here, that padlock belongs to you. The key has your name on it, the padlock has your name on it, and only you're allowed to take it. So you put the components inside the box that are necessary for the vehicle to run, like the key or the service plug. If that's not possible, you can also have this type of tag, so to say, which goes over a very obvious place so that anyone really has to be stupid to start the vehicle. It says on there quite clearly, don't touch this vehicle. Also, you might be required to have a buffer zone around the vehicle, so put out cones around the vehicle so that it's quite clear, stay away. And also you've got the caution, high voltage, don't touch. So print that out here, fold that up and stick it on top of the vehicle. Again, different countries have different requirements for the different types of signs. You might see that, but put that in various areas on front of the steering wheel, on top of the vehicle. You don't want people, it's not just to protect yourself, but to protect others as well. When it comes to some of the other components as well, we want to make sure our equipment is category 3 rated. So that will be usually on the back of any of the equipment that we have, back or the front, but that's the minimum standard that you need for any type of measuring equipment. So you might see voltage testers like this, you might have your multimeters, insulation testers. All of those need to be minimum to Cat 3. Now, insulation tester is something that we're not usually used to in the automotive industry. So insulation tester is something that can give us 1000 volts. So across the two terminals that you see here for the what looks like a normal multimeter, we can use it as a multimeter, but we can also give out 1000 volts here at the measuring terminals, and that will actually break down any of the problems that we might see in the insulation for the motors, for the cables for the motors, sorry. So if I just show you on the screen here what that means. So this is just showing a normal ohm meter to one of the cables, so one of the phases on the electric motor to ground, and you see that it doesn't affect it at all. Now if we change that to 1000 volts, so now we're putting 1000 volts through those cables, and at that point the cables are breaking down. There is a bit of the insulation either has a pinhole or it's been damaged in some way, that once we put it under that sort of stress, then we see the problem to ground. So I'll just show you that as an example, what we would do there. So on this system here, we've got some faults that I can bring into the system. So we can either see that here. So driving along, and we get an insulation fault. The system would shut down. So depending on various types, again, most manufacturers have slightly different variations on the way the shutdown procedure works. So if you're driving along, the vehicle will not just stop on you. Sometimes, depending on the severity of the fault, you will have a chance, the little triangle of death will come up saying, okay, pull over or go straight to service. Sometimes once you pull over and stop the vehicle, you can't start the car again. Sometimes you can. So again, every manufacturer will be different. But what we're showing here is, okay, high voltage fault, vehicle has shut down. Now, what we can go here is, okay, it's telling me here the insulation resistance is too low. So, what would we do in this situation? So that's just the fault section. Now, getting the student to have some sort of procedure, what they're doing for shutting down the vehicle, how to test for this fault, and have some sort of diagnostic strategy. So we've given them a chance there, okay, read the fault code here. What do we do now? Okay, so we need to shut down the vehicle, of course. So this procedure that I was going to show you. So shutting down the vehicle, either keep the key, don't throw it on the ground, keep the key in a lockout box or in your pocket. So I like to say to my students, it's your life, it's your responsibility. So keep it there. Again, smart key needs to be put away from the vehicle. Now, we need to test our gloves. So we're checking the stamp, checking if they're holding air. Now, we also need to do what's called the dead live test. So that's when we get our multimeter, and we're going to check to make sure that our multimeter is actually working. Because if we've got a faulty multimeter, the fuse is blown or something, and it just says 0 volts, and we actually go along and we check the high voltage connection, and it says 0 volts, but it might have 200 volts on a battery voltage, but due to a faulty multimeter, we've just got a false positive, or a false negative rather. So very first thing we need to do is with a real battery. Now we want to check the same type of voltage. So here we're using DC. We'll be testing DC high voltage, but at least we're testing DC here. So I've got a 12-volt battery, and that's shown up, works good. Okay? So I've tested my gloves, put them on. If we've got leather over gloves, put those on as well. Unfortunately, these are too small for my hands, but you get the idea, we put them on. We've taken the ignition key out. Now we can go along and find the service plug, and we can disconnect the service plug as well. Again, if you've got a lockout box, it goes into the lockout box or it goes into your pocket somewhere. Some manufacturers will tell you to insulate the connector left on the vehicle as well, so get some insulation tape and wrap around it. It's up to you, up to what you're required to do. Now, on every vehicle there will be a measuring point where you can go along and measure a connection. So this here is simulating inside the inverter where we can disconnect the cover. Now inside this cover is a interlock, so if you were to disconnect this, the power would shut down. But due to the large capacitors inside the vehicle, it can take some time to shut down. So we need to go along and measure the connectors. So I've got two connectors here coming from the high voltage battery, and right there is now 0 volts. So the time it's taken me since I've shut down the ignition, had those capacitors discharged, there is 0 volts right here. Now I'm not quite ready yet. I need to go back to a live dead live. So I'm going to go back to my battery, 12-volt battery, and check to make sure that my measuring device is still working. That didn't blow it up measuring the high voltage. And yeah, I confirm that this battery now, this measuring device still works. At this point now, I'm satisfied that the vehicle is shut down, fully isolated, and I can now remove the gloves. Okay? Obviously at this point, the high voltage battery still contains high voltage, but the rest of the vehicle is safe. Now, we're going back to that insulation fault. So, to show the difference, what actually happens, we showed an animation, but you can actually have a look here and see what happens. So, here I'm measuring across the various phases of a motor. Phase 1. So, and nothing, no change, I can't see anything, but I know there's a fault within this system. So what I need to do here is I can change that to 1 kV. And when I press test here, now we're actually putting 1000 volts into the system. You see now, we've got the system come up that's found that leak. So, now of course that's a bit harder on a real vehicle. You need to remove all of the cables individually. You can test each of the cables, test the motor, all of that. But this is just getting the students used to using this type of equipment and showing how it works. Okay, so for at that point, we say to the student, okay, yep, you've got that. Teacher can come along, remove the fault, and then we need to put the vehicle back. So, gloves go back on. Once we've got the connector back in, the cover back on, we can go back in now, reset, and of course you would drive the vehicle and do a road test. Okay, so if we have a little bit more look in detail at some of the technology, so various battery systems. We've all heard about some of the vehicle. There's a lot of worry out there about lithium batteries. There's a condition called thermal runaway. So thermal runaway is basically a vicious circle. Once a lithium type battery once it heats up, it causes a chemical reaction which causes further heating, and that builds upon itself until a point where the battery can actually catch on fire. They have so much energy inside that they can catch on fire. Now most manufacturers, the battery chemistry is changed with more stable elements so that they don't catch on fire so often, but it has happened in the past. So you see that here with this mobile phone battery, just got stabbed and all of a sudden catches on fire. Most of that's taken care of now. They take great detail in making sure that these batteries are protected, physically protected from damage, but also protected from heating up too much. So lots of cooling occurring on the battery. Sometimes they're even heated as well. Various types of batteries. So you see here, this is a prismatic cell. So this is what you find in the Toyota systems, nickel metal hydride. And the important thing here is that the batteries, each of those cells are connected in series, and so that they build upon themselves. So each cell works on one another, and that's how we get the voltage. So from each of those nickel metal hydride cells at 1.2 volts, each one of the modules has 6 cells, 28 modules, looking at 201.6 volts. Depending on the different type of battery, might have more cells, less cells, more modules, less modules, but important to note is the way they work. Service plug, as you'll see here, is actually disconnecting the battery. So not only disconnecting the battery from the rest of the vehicle, it's disconnecting the battery into 2 separate pieces as well. And we can see that right here, that these 2 cables go off to the service disconnect. And when we disconnect the cable, we're actually disconnecting the battery into 2 complete different parts. So we're also dropping the voltage of the battery down into an even lower voltage, making it safer again. Okay, so some of the different types of batteries that you'll see in hybrid and electric vehicles now is, for instance, the round cell. So this is very similar to a D-cell construction, so cylinder, and basically exactly the same size, and these are then welded together into sticks of 5 or 6 size, and then they're packed into, so that's then called the module, and then they go into the complete battery pack as well for voltages up to 300 volts, for instance, all in series again. You see Tesla doing something slightly different with the system, so now they're running in series and parallel, so they're using a much smaller battery called the 18650. They've also upgraded now to the 2170 battery, so that refers to the size of the battery in millimeters. But you can see that the battery here is now much smaller, but there's thousands of them. So in each of these modules here, so we've got 400 modules in there with up to 14 modules in each of these battery packs. So there can be up to 7,000 of the individual battery cells. We've also got pouch cells. Oops. So a pouch cell is also a battery pack. So again, depending on the chemistry involved, but we've got these of up to 4 volts, 3.5 volts or thereabouts. Again, a battery cell, battery module, and then together into the battery pack. So these here are both in series and parallel. So for capacity and to increase voltage. Here we see the Chevy Volt, and that's also using a cell, pouch cell. These cells are then built in together into these modules, and what you see within the modules here that they have cooling fins as well. So there's actual coolant running through various pouches inside, so not inside the pouch cell, but next to these cells is a coolant chamber which allows some coolant to run through, cooling down the batteries. And these cells can actually build up because they're sealed, there's no vent on these, they actually can expand when they get a little bit older. Some of the built-in protection that we see within the various types of batteries. So here you see inside the service plug, you can pull the plug apart, and inside that plug you'll see the fuse. So that's one of the areas where we've got some protection. We've also got the interlock there. If you look on the Tesla version, we're actually seeing that there's tiny little fuses on every single one of these cells, and that's called wire bonding. So if there's a short circuit within that individual cell, that will just blow that one fuse. So, and because there's so many in series and parallel, by having one of those drop out, we will drop capacity, but we won't drop complete voltage or thereabouts. Battery management system, there's lots of different types of things that are being tested in the battery at the same time. So state of charge is something that's very important for the vehicle. So we see here one of the main differences between your normal battery that we see here. So we've got just your normal battery you buy at the shop compared to a battery found in a vehicle. So you see here, the batteries can be flattened completely and then charged again. So either completely flattened. What we see in an electric vehicle is though, just go back there again. We're operating in a very narrow band. So we're not completely using the capacity of the battery. We're not starting to fully charge to fully discharge. We're operating within a very narrow band, roughly between 50% to 80%. Again, every vehicle might be slightly different, but that's to ensure that the battery is not being overcharged or undercharged or discharged, which is going to greatly affect the service life of that battery. So this is what manufacturers are doing to keep the batteries lasting for 10 years or more. So some of the different systems that are being tested within these batteries, we need to test for voltage. So you'll see voltage sense wires on various cells or modules. Again, most manufacturers will be slightly different. In this case, it's just a simple wire which is going back to the battery management system. We've also got current sensors. So current sensors can either be a shunt type or they can be a Hall type of current sensor. So as you can see right here is one of the current sensors. You've basically got the cable or the conductor going through the current sensor itself, and it can then pick up through the magnetic field, it can pick up the amount of current that's flowing through there. Temperature sensors, also very important, which then obviously affects temperature management. One of the important things as well is shutting off the high voltage system. So how do we disconnect the high voltage system from the rest of the vehicle? So we've got the high voltage disconnect relays, sometimes called contactors, sometimes called system main relays as well. So very important system. There's sometimes 2 relays, sometimes 3 relays. The important thing to know, we've got here, when are they open and when are they closed? Very specific. I'll just show you these here. So this is the relays right here. In this case here, we've got 2 on the positive side, 1 on the negative side. And we've got this little resistor here. So when we first press the start button with a brake, so we're now going towards the ready light. If you've ever driven a vehicle like this, you'll notice the ready light takes a little while for it to come on. What's actually happening is we're going through what's called the pre-charge relay. That pre-charge relay is slowly, it allows the vehicle to build up the current slowly. And there's a couple of reasons for that. But I'll just continue here. So it allows that to happen first. Once those conditions, a few conditions are met, it then opens the main relay. And you see there's no resistance there now, so now we're available for full current to be available at the inverter. So that's important if we see here. Now if we were to have either a short circuit, a good example is inside the air conditioning compressor. If there's a short circuit, you've just replaced it, put a new or sometimes even a used air conditioning compressor onto the vehicle. If there's something wrong with that, let's say we've got a short circuit within the air compressor or in the inverter, then what's going to happen, without this relay, we're going to get full power going to the short circuit. We know that when we have a short circuit without any resistance, we're going to get full current that's available from the battery going through that circuit. And that's going to create some pretty massive damage. It will melt all of the cable, all of the wires, destroy the system. So that's why we use this pre-charge relay. It also allows the capacitors inside the inverter to slowly build up, because they can really suck in a lot of power all at once. So what happens here, if the system realizes there's a fault, it won't shut on the second relay. It'll allow the first one to open. It'll shut down the system after recognizing a fault. So I can recognize that also through the current sensors. Now, some of the conditions that you need to have is when the relays are open, when the ignition is off. So that means if the battery is disconnected, the 12-volt battery is disconnected, these relays should be open. If the airbags have been deployed, the system will open the relays as well. So even if you disconnect one of the airbag connectors on one of these vehicles, the system will shut down. So you need to have a scan tool and actually remove those codes before the vehicle can be started again. If the interlock has been interrupted, that will also shut down the vehicle, so open the contactors, and if there's certain faults within the high voltage system. So only when the interlock is complete, when the ignition is on and the high voltage system is fault free, is when it will close all of those relays. Okay, so I'll jump down now to some of the power electronics. So this is really where the technology comes in for electric propelled vehicles. So it's basically a good idea to have some of the different parts that you have. You can have these in your classroom as well. So these parts are getting easier and easier to access. Basically the vehicles are becoming cheaper and cheaper, so you can have a vehicle and maybe wreck that, have it in your classroom. pull it apart, have the various components. You can ask manufacturers, you might get some stuff donated. So having all of this on hand is always good to have. So cables within the high voltage come in two different types. So you could have a complete cable which has just one cable, so to speak, within the whole conduit, and that is, say for instance, one of the phases to the motors. You also get here, you'll see this multiple core cable. So you might have, for instance, where I was talking before about the air conditioning compressor, all three phases might be inside one cable. You might have also the battery cable coming from the front and rear, might have the positive and negative in one cable as well. It's also very important to know that there's shielding inside, around each of these cables as well. That's what we're showing on this circuit diagram on the thing here as well. So that's to ground, and that's to stop any electromagnetic interference. Now, electric motors. So we're showing here how can we get an electric motor to turn. So we've all heard about the three-phase motors, and basically we're using electromagnetism to create a magnetic field which allows the magnetic field to rotate. Once we've got that rotating magnetic field, that will, through various means, if we've got a permanent magnet rotor or if we've got an induction motor, will then follow that magnetic field around. So you see here, one phase, what happens when we change direction of current, so AC, we can see the magnetic field being either drawn towards the coil or pushed away. And by blending those three together, we can then see this rotating magnetic field. Once combined with the rotor, we can then create this field to turn around and turn the rotor. Now, various types, as I said before, permanent magnet, also called a synchronous motor. They're the type with permanent magnets, so they've got magnets inside the rotor. These magnets create the north and south poles, and they're following the magnetic field. That's relatively easy to understand. And when you see a motor like this, we can show what that means. So here we have the three phases with the various coils that are made around that stator. And it's basic to see how they work together. All those three phases work together just like that. Now, what's a little bit harder to understand is an induction motor. So they don't have any permanent magnets inside of them. Sometimes also called a squirrel cage. Basically, what we're doing is we're creating an electromagnet within this rotor. So the rotor has, it's called bars going through the rotor, and they're short-circuited on each end of the rotor here. So as we create the magnetic field in the three coils around in the stator, that creates or induces a current inside the rotor, which then in turn creates a magnetic field inside the rotor. Once those two magnetic fields correlate, the rotor will begin to turn as well. One of the very important things, it's very important to understand how the magnetic field, how the motor will turn around. So it's very important that the inverter inside the vehicle understands exactly where the rotor is. And so for that, we need a rotor position sensor, so also called a resolver. So the resolver is made up of three different coils, and we can see here that as the rotor turns around, it's creating an induced voltage, which then will create two separate waveforms in the two watching coils that are surrounding the resolver. So it's made up of these three different, so cosinus and sinus, and depending on where the resolver is, where the rotor is turning around, and the inverter can sense exactly where the rotor, the inverter can sense exactly where the resolver, the inverter can sense exactly where the rotor is, and so it can turn on each of the various phases exactly as it needs to be. If the resolver wasn't there, and the motor or the inverter didn't know exactly where the rotor was, once you turn the engine on, it wouldn't know, and it's possible that the engine could, the motor could start turning. So it's very important that it's there. It's not an encoder. An encoder is a Hall sensor, and it needs to start turning to establish the position. This will work when the motor is not turning whatsoever. Okay, also with regenerative braking. So here we've got a current clamp connected to the battery itself. And we can see, okay, so as we're driving forward, we can see the amount of current flowing out. So here we've got 25 up to 50 amps flowing to the battery, to the motor. Now we're in the negative phase, so you can see it's instantly going back, it's regenerating, and now we've got 23 amps going backwards into the battery. So it changes quite a lot depending on how much acceleration you're putting in. So there we've seen about 90 amps, and the maximum going backwards was about 60 amps back into the battery. And that's all from regenerative braking. Now, one of the main questions is how do we get, so we need to create an AC sine wave to create the three phases, but how do we do that when we've only got a DC power supply? So here we're seeing the inverter. This is a simplified version of the inverter signal, and we can see the average of this pulse width modulated signal is the voltage. So that will affect the amount of current flowing through that circuit. We can see that the sine wave is being created there. Now, that's easy enough, but we've only got a DC power supply. So we also need to find out how can we create a negative source from a DC supply. So what we've got here is a very simplified circuit. We see this resistor. This resistor is simulating our motor. So the motor has windings which have a resistance. And we can see here, so with the power supply we've got a current flow flowing around in this circuit. Now if we go on the bottom side of this circuit, now we're opening switch number 2 as opposed to switch number 1. We can see that the current obviously still flows in the same direction, but now the resistor is at the top of the circuit as opposed to the bottom. And what that does is we can see the effect here on the oscilloscope is now we're creating a negative voltage just by switching those top and bottom switches. So what that effectively means is this here. So we can see the current flowing through, and it always flows through two phases at the same time, so two windings. So we've got the DC positive at the top here going through this IGBT through one of the phases back out. And so it's depending on which of these IGBTs is being switched. In this instance, they're being switched on and off to create the digital sine wave here. And we see there, now we've switched direction. So before it was this one, now we've switched to this one here. And it's still going through the same two phases, but it's just in a different direction. And you can see there, now we're getting that switching between positive and negative. And the time that those IGBTs are switched on is the amount of time that we see here. Now, of course, that's super simplified. That's occurring around about in between 8,000 times per second to 16,000 times per second. This switching is occurring, so it's extremely fast. Now, what that looks like on a real vehicle. So this is taken off of the inverter signal from a Toyota Prius. So you can see here now that's, as I said, extremely fast. It's around about 8,000 times per second. We've got 200 volts per division here. So 200 volts is there, that's 400, 600, 800 volts. So as the vehicle drives along, so unfortunately it's a bit shaky here, but you can see now we've got this block. So that's the digital switches, transistors being switched on and off. And it's a bit hard to tell because of the speed of the system, but the pulse width of those is changing. So now we're going to see that AC. So if we were to measure the current on the oscilloscope, we would be able to see the current. So measuring across the resistor, we would see the current flow going through there. And you can see that varies quite a lot, from 200 volts here up to 700 volts. What is happening there is we see frequency is obviously related to speed. The faster that frequency is occurring, the faster the motor is turning. The amplitude, however, is controlling the amount of torque that is required. So the amount of torque through acceleration, more torque is required, more amplitude, so more voltage to push more current to create a bigger magnetic field. That's what we see there. And that's what I meant from earlier when I said that it's not a simple 200 volt battery, 600 volt output. It's varying all of the time in between those two values. Some of the capacitors that we spoke about before, sometimes they're quite obvious in the inverter if you have a look. So some of the older Priuses, they were right here inside once you open the inverter. A lot of the newer ones you can't see where they are, they're hidden. So they're basically in this unit here. We've got this X-ray that you can see inside there's 3 capacitors here and 2 extra ones on the side. They can be discharged through active or passive means. So active discharge is when we can see that here. This section here is the resistor being turned on. The very first one, when we've got the resistor in line, you can see it's very slow, well not very slow, but you can see there's a ramp up period here that's going through the resistor. Right here, there's a tiny little switch. That's the second relay being turned on. And we'll see right here, that's the vehicle being switched off again. And there's a little step occurring right here. What that is the inverter actually discharging through 2 of the windings in the motor to discharge all of the built up voltage within the system. That's called active discharge. Some of the older vehicles have what's called passive discharge, which is just through a resistor in the system. Okay, so some of the measurements that we can take on this unit to show some of those theories and that we've just had a look at. We've got all of the measurement devices built in here, and we can take some of the different measurements from each of these measurement points here. So for instance, if we're looking at motor generator 2, we can have a look at, for instance, the motor generator being driven, or even in freewheeling mode. So if you see the sine wave like this, as it's freewheeling, so it's being driven by the first motor here, we can tell that it's a permanent magnet motor. If we have a look at so we can see here also battery voltage, so I've got a voltage division here of 100, so that's around about 45 to 50 volts. If I take it up the top, you can see here over 300 volts. So this system has the buck boost converter, converting it to a higher sync. So one of the other things that we can have a look at is the charging of the systems as well. So what is the communication within the vehicle and the supply equipment? So we've got this system here to show how the vehicle may be charged. So we can see here there's a number of conditions. Again, depending on what type of connector you have, so if you've got type 1 connector or the type 2 connector, depending on which country you're from, there's different types of things that you need. Because the type 1 connector that you see here has a switch, there's no need to lock the vehicle. But in a lot of the European countries, you can see that there is no switch on the connector. So basically, if there was no switch, you could pull it out. So this system is now locked in. So it happens when I've turned the vehicle off and even locked the vehicle. Once that's done, once those conditions are met, the system is locked in there. With the type 1 connector, there's a switch inside. So when I press the switch to undo the mechanical lock, it also shuts the charging off. So there's no need to lock the vehicle in this instance. But just to show some of the communication that's occurring. So here we see the pulse width modulated signal that the car is reading. And this is what the vehicle is reading. So we're seeing here bipolar, it's on both sides. Within the vehicle itself, that is the same signal, but it's being rectified. So we're seeing this here. Now, there's various means of what this actual signal is telling us. So on one side, there's the pulse width, the actual how long the duty cycle. And also the voltage varies as well. So 12 volts, 9 volts, and 6 volts, depending on the condition, if the vehicle is ready to start. Also the amount of duty cycle is telling the vehicle is telling the supply equipment what is the maximum charge the vehicle can take at that point. Okay, so there's a lot that can be shown. Can spend hours and hours going through this. There's roughly about 20 hours of curriculum, courseware that we have here. Obviously we don't have that sort of time, so just wanted to show you some of the things that are available, some of the things that you can do in the classroom. Of course, this is not to replace a real vehicle, this is just to help and guide the students along as well. It's always best to have the actual vehicles in the classroom and or in the workshop. Yeah, so again, if you'd like some more information, put down your email address and we'll get some more information out to you. So thanks very much for your time, appreciate it, and all the best. Thanks.